A uniform annulus is a uniform disk with a hole cut out at the center. The radius of the hole is b, the radius of the overall annulus is r. Now we will calculate the acceleration of such an annulus down an incline of angle theta. We will find that the acceleration of the annulus is independent of the mass, so it doesn't matter what the mass is. We could change the mass and the acceleration would be the same. Now we will also do something that's very interesting. We will compare the acceleration of an annulus to a disk, a uniform disk, which we covered in a previous video. We will find that regardless of the size or mass of the disk, or the size or mass of the annulus, that by size I mean including both radii, the size of the hole or the overall size of the disk given by r, the disk will always win. It will always reach the bottom of the incline first. In other words, the acceleration of the annulus is always less than the acceleration of the disk. So we have the acceleration of the disk from a previous video. We know that it's independent of the mass and the radius of the disk. So we could line up a disk of any size or mass next to an annulus and it will always win the race. And that's true no matter what r and b are and the mass of the annulus is. Okay, so let's run through the resultant force in this object. So I'll go through this quickly because in the previous video we essentially went through the same steps. So in red I'm showing the forces acting on the annulus. In the other colors, like blue here, I have a component. So to get the resultant force, we get the component of the weight down the incline, mg sine theta, and subtract the friction force F. And we know that that's mass times acceleration by Newton's second law. So I explained in the previous video, and I'm not going to go through it here, that the friction force is the moment of inertia of our annulus about the center, okay, times a over r squared, times the acceleration of it down the incline divided by the radius of it squared. So this will work out for an annulus as it would for a disk. It's the exact same reasoning as for a disk of radius r. So we're dealing with an annulus that's rolling without slipping. Okay, we show that alpha, the angular acceleration about the center, is the linear acceleration divided by the radius squared. And we just plug that in here and we rearrange to get the acceleration down the incline. So we just do a bit of simple algebra. Now the difference here, of course, between the acceleration of the annulus and the acceleration of a disk is in the moment of inertia of an annulus about the center. Now I covered this in another video, so I'll just quickly go through it here. So what we do is we get the moment of inertia of a full disk of radius r. Okay, so let's say the mass of the full disk is md, because m stands for the mass of the annulus. So the moment of inertia of a full disk is a half the mass of the full disk times the radius of the full disk squared. And what we do is we subtract out the moment of inertia of the piece that's removed to create the hole. So the mass of that we will call mh, h for hole, and the radius of that piece is b. So I explain this in another video. It's just the fact that moments of inertia involve summations. So when we remove a piece of an object, the moment of inertia decreases by the moment of inertia of that piece. So you can also do this using going back to first principles for calculating moment of inertia and using integration, but that's another video. Now what we do then is we relate the mass of the disk, a mass of a full disk, and the mass of the piece that was removed to make a hole to the areas, okay, because we're dealing with uniform objects here. So if we take the mass of the disk, full disk, and say divided by the mass of the annulus, which is just m. Okay, so I'm indicating, the weight of the annulus is mg, the mass is m. So if we take the ratio of the mass of the disk to the mass of the annulus, we get the area of a full disk, which is pi r squared, divided by the area of the annulus. Well, the area of the annulus is the area of the full disk minus the area of the hole. Okay, this is because mass is proportional to area. So obviously we want everything in terms of m. So m is what we're using for the mass of the annulus. So we don't want these new terms md and mh to come into this. Okay, so that's md, and of course we do something similar for mh. If we take mh and put it over the mass of the annulus, it's the same as the area of the hole, pi b squared, over the area of the annulus. Just pi times r squared minus b squared. Alright, so then we just, you can see now that the mass of the piece removed to make the hole is b squared over r squared minus b squared times m. Okay, so let's plug everything in here. So we want IC, so it's a half times MD. Well, here's MD in terms of M, R squared over R squared minus B squared times M, minus a half times MH, which is B squared over R squared minus B squared, and that's multiplied by M. These M's cancel. Now I'd factorize a half out of the top of this thing. Now I nearly forgot, of course, that we've a half md times r squared here, and we've a half mh times b squared. So to multiply this by b squared, so that means that this becomes b to the power of 4, of course. Actually, this becomes r to the power of 4, and this becomes b to the power of 4. Okay, so I want to put these two fractions together. Common denominator r squared minus b squared, so we have r to the 4 minus b to the 4 on top. Now r to the 4 minus b to the 4 is the difference of two squares. It can be written as r squared squared minus b squared squared, and we know how to factorize the difference of two squares, so we can write what's on top as r squared minus b squared times r squared plus b squared. So that's convenient, because these go out. So we end up with r squared plus b squared divided by r squared. Well, breaking that into two fractions, we have r squared over r squared, which is 1, plus b squared over r squared. And of course we can write this as 1 plus a half b squared over r squared. So that's going to give us 3 halves plus a half b squared over r squared. So there we have it, the acceleration of an annulus of inner radius b and outer radius r. It's independent of the mass. No m's appearing in this. And notice that it's always less than this quantity here, because the denominator, the only difference between this and this is this quantity here, of course. But this thing over here is the acceleration of the disk. So the acceleration of an annulus of any mass or any inner and outer radius b and r is less than the acceleration of the disk. So it doesn't matter what b and r is. B is always less than r, of course, but you know, this quantity here is always some non-zero term. It's always some term that we're adding onto 3 halves. So this overall thing is always going to be less than the acceleration of a disk, a uniform disk of any. Again, the disk can be of any radius or mass. So this is really surprising in my view. Somehow simply taking a uniform disk and cutting a hole in it changes everything. And even if we can't even compensate for that change by increasing the mass or increasing the outer radius, there's no way we can make this annulus, make the acceleration of this annulus greater than or equal to the acceleration of the disk. It's always going to be less than the acceleration of any uniform disk. Now we can see that this formula makes sense for the acceleration of an annulus if we say let b equal 0. If b equals 0, well, we don't have any hole. If the radius of the hole is 0, then basically we have a uniform disk. So we get 0 over r squared, so that just disappears. So we end up getting g sine theta over 3 halves, which is the acceleration of a uniform disk. Okay, so that checks out. That makes sense. Okay, so we get the acceleration of a disk. Now let's consider the situation where we let the radius of the hole approach the radius of the annulus. So let's imagine if we take the limit as b approaches r of the acceleration of the annulus. Well, we're going to get g sine theta on top, of course, but underneath we get 3 halves plus a half times r squared over r squared. Well, that's just 1. So we get a half times 1. Okay, so the limit as b approaches r is going to be this thing here, which is g sine theta over 2. So what do we end up with? Our shape is a hoop where all the mass m is in the rim. Okay, because now b is equal to r. So this is going to be the slowest annulus, okay, because we've maximized the ratio b over r by letting b approach r. B can't get any bigger than r. We've maximized this denominator. So the annulus with the smallest acceleration is a hoop of radius r.